So now let's try correlation testing.
We'll still state the null and alternative hypotheses. We'll still get a critical value. But this step where we determine the critical value will come from a slightly different chart. The calculated values from step 3, well, you could use that ugly formula I showed you in the last video, or you could use, for the calculation, our good friend Excel. The drawing, rejecting, and interpreting will remain the same. If our critical value of R is positive, it lies to the right of the mean, we still have a rejection region, and we'll have to determine if our calculated Excel value falls there. Likewise, if we have a negative correlation, then our critical R will also be negative, below the mean, and to the left. We still have a rejection region there also. Here's one version of the R chart that you might see in your homework, and here is a not so great copy of one you might see in a book. Their proper name is the Pearson Product Moment Correlation Coefficient chart. I'm going to cut that down and just call this the R chart. So let's work with this chart a little bit. Let's assume that we had some data and Excel gave us a calculated value of 0.52. There were 19 data pieces in your study, and you want to know with alpha equals 0.05. We have to find the critical value and then compare them. Here we have 19, and it's n, not a degree of freedom. And we're reading at alpha equals 0.05. My critical value is 0.456. So comparing the two values, my critical value, which comes from the chart, would be 0.456. Here's my rejection region. My calculated value is 0.52. Do I have statistical significance? Is my calculated value more extreme than my critical value? Yes. Another one. Again, we're going to say that R equals 0.52, N equals 19, but this time let's read 1% significance. We're willing to be wrong 1% of the time. Now I'm going to read 0.0575. Drawing this picture, 0.575, and my rejection region. My calculated value of 0.52 would be back here. Do I have significance? In other words, is the calculated in the critical region? No. Here we have a negative value. N equals 35, alpha is 0.01. N equals 35, alpha equals 0.01. My critical value, 0.430. So draw this one, but be careful. The original value is shown as a negative. It's going to be below the mean. None of those R charts have negative signs. So I'm going to need to assume, I know, never a good idea, but here I have to, that this is also going to be negative. Negative 0.430. Here it is, my rejection region. Where does my calculated Excel value fall? Negative 0.44. Is this in the rejection region? Yes. So in correlation testing, you have statistically significant evidence, or enough evidence to show a statistically significant difference between the calculated and the critical value. If the calculated value is in the rejection region. Correlation testing is understanding the way that we write the hypotheses. It's a little bit different in that we use a different symbol. Remember? Correlation coefficient in the population is that funny looking P called rho. If we happen to have a two-tailed test, we're going to have not equal and equal, meaning there is a relationship for HA. It's not nothing, it's something. If we were to go to a left-tailed test, left being below the mean, our hypothesis would say less than. Then the null hypothesis would go the mathematical opposite, greater than, and have its equal. And last but not least, if we had a right-tailed test, we're looking at numbers that are positive for our hypothesis, and the null would say less than or equal to. So let's try one of these. The absences and its relationship to the final grade. Is this a statistically significant relationship? So head back to our good friend Excel, Data, Data Analysis, Correlation, click on the data and the output range and hit OK. We have an R value of negative 0.84536, a strong negative. In the problem I worded it, is there a statistically significant relationship? I didn't say positive or negative. I just said, is there one? It's not zero. That's what I think. In the null hypothesis, we would say, as always, the equal. And these are now mathematical opposites, which is what we want. So now we have to go to the R chart and find our critical value. In the Excel file, there were 16 pieces of data. I didn't tell you alpha. By default, when you're not told what alpha is, it will be 0.05. So those are the two pieces I go find in my chart. R equals 16 at 0.05 for alpha. My critical value is 0.497. My calculated value, again, this comes from Excel. Going back to the data, R was negative 0.845. Negative 0.845. Yes, that means this also needs to become a negative for our comparison. In our comparison, our bell curve, here's the mean, negative 0.497 would be here. Shaded is our rejection region. Negative 0.845 falls way over here in our rejection region. We will reject. Color coding that a little better for you. You can see the calculated value falls in the rejection region as determined by the critical value from the chart. We reject the null. Now we interpret the statistically significant relationship between absences and final grade.
So if I want to find a relationship between two things, keyword relationship, I'm going to run what's called a correlation. Do I think that there is a relationship in the population, rho, that is not a nothing? Do I think there's something? The mathematical opposite, rho, equals 0 for the null. The null always has the equals. Here I'm going to set alpha, the part I'm willing to be wrong, at 5%. To get my p-value, the probability that I am wrong, that it's by chance that I have sampling error, I go to my data set and I choose Data, Data Analysis. If I want the correlational value, I input my range, and that tells me that I have a strong negative, but it doesn't tell me p-value. To get that, I must go Data, Data Analysis, Regression, and OK it. What happens second? The dependent variable is the final grade. That would be my y. What happens first would be my independent variable, the x. Data, Data Analysis, Regression. Here I see the same number, but there's no negative sign, so be careful when you choose regression. I have an r-squared value, which tells me that 71% of my final grades are explained by absences. But in this case, since I'm doing a correlational test, I'm looking for the p-value, the probability that I have rejected a correct null. Very, very small. 3.7 e to the negative 5. That means I would have 3.7 to the negative 5 power. 1, 2, 3, 4, 5. Those would all be filled in with. So I ask myself, self, is p, which equals 0.000037, is that less than alpha, which is 0.05? My answer is yes, that is smaller. Therefore, I will reject the null. For my next example, I think that there's a positive relationship in this scenario between a mother's birth weight and her baby's birth weight. I think it's positive. So I think the relationship in the population is greater than 0. Numbers that are greater than 0 would be positive. In contrast, HO, the null, would say rho, the correlation in the population, would be less than for its mathematical opposite. Null always has the equals, 0. I'm willing to be wrong, or alpha, at 5%. I want to see if there's a relationship between a mother's birth weight and her resulting daughter's birth weight. I want to see if there's a relationship between a mother's birth weight and her resulting baby's birth weight. If the mother is large at birth, will the baby be large at birth? If the mother is small at birth, will the baby be small at birth? I think that there's a positive relationship here. I think that in the population, the relationship will be bigger than 0. It will be a positive number. The null then would say the relationship would be negative or equal to 0. I'm willing to be wrong 5% of the time. Graphically would look something like this. 5% of my curve being shaded for a rejection region. My p-value would be from data, data analysis, regression. The y is what happens as a dependent. A baby is a dependent. The x is what happens first, the mother. Then I choose my output range and I OK it. My p-value is 0.106. But that p-value, since I'm only dealing with the positive, has to be cut into 2. So 0.053 would go in each half. 0.053 would be from the calculated value, the t statistic backwards. And it would also be the same over here. 0.053 to the left. Why? Because those two added together give me that 10%. So when I compare them, I will take my p-value, which was 0.053, and ask, is it less than alpha, which is 0.05? And I would say, no, that's not true. I cannot say I'm right. At this point, the birth weight and baby's birth weight. So now for our last one. We want to see if there's a relationship. It doesn't say positive, it doesn't say negative, it just says linear. Is there a relationship between the number of tickets that a student receives and their GPA? I think that there is a relationship. It's not a nothing, it's a something. They, the null, would say mathematical opposite, and null always has the equal 0. We're working with the default of 0.05, so that's alpha, that's the percent we're willing to be wrong. To get this printout, I would have gone to Data, Data Analysis, and then touched Regression, where I would have used X as my number of tickets, what happens first, Y as my GPA. When I get that value, I come up with a p-value of 0.021. That means that from my calculated t-statistic to the tail, I would have 2% of my curve shaded. That would force me to be in the rejection region. So is p less than alpha? Is 0.021 less than 0.05? Yes, it is. That would again force the t-statistic to be in the rejection region. And therefore I would reject the null. Nana nana boo boo, I'm right, they're wrong, and I should interpret it.